In the Red Sea, some of the most advanced warships in the world faced an enemy they couldn't escape, not an opposing fleet, but wave after wave of low-cost drones and missiles appearing over the horizon. In just a few months, the U.S. Navy burned through nearly $1 billion worth of interceptor missiles, not to win, but simply to stay afloat. These targets didn't need to score a hit. They only had to force radars to stay active, compelled defensive systems to lock on, and trigger the launch of interceptor missiles, costing millions of dollars each. Modern warfare is no longer measured by how many targets you destroy. It's measured by how fast you're burning money. The Red Sea exposed an uncomfortable truth. Even the most powerful fleet can be worn down, not by superior firepower, but by sustained economic pressure. And when groups like the Houthis can maintain that pressure, every nation dependent on the sea understands one thing: no one is outside this game. Japan understands this, and Tokyo knows it cannot win a war of attrition using expensive missiles alone. So, it's betting on a different option: laser weapons. Chapter 1: Japan's Strategic Turning Point. In late summer 2025, at JMU Isogo Port, Japan's sea-based railgun testing was complete. The test vessel JS Asuka removed the entire gun mount, but the empty deck didn't stay empty for long. In early December 2025, a new system appeared: a 100-kilowatt high-energy laser weapon developed by Japan's Acquisition Technology and Logistics Agency in cooperation with Kawasaki Heavy Industries. This wasn't a routine hardware update. It marked a strategic shift toward directed energy weapons. Japan didn't choose a public demonstration. Instead, it moved quietly to operationalize a doctrine built around a single survival question: how do you defend a fleet against swarms of low-cost drones without exhausting your national defense budget? Built around 10 fiber laser modules combined into a single beam, the system is designed to serve as an active maritime defense layer beginning in 2026. Chapter 2: Geopolitics and the Attrition Trap. To understand why Japan is moving so quickly, look at the geopolitical map of 2025. Japan has been steadily reinforcing a multi-layered defensive network across the island chain from Kyushu to the southwestern approaches facing Taiwan. Yonaguni Island, just 68 nautical miles from Taiwan, has become a forward line. As Chinese naval vessels and combat aircraft increase their presence, the operational environment has grown increasingly constrained. But the pressure isn't just from large-scale attacks. It comes from persistent harassment by targets that are low, slow, and small. Each radar warning triggers the same dilemma. Is it worth launching an interceptor missile costing several $1 million to destroy a drone worth only a few thousand? This is the economic trap of modern warfare. The 2020s marked a shift from sophistication to practicality. Quantity is becoming a form of quality. By 2025, Ukraine set a goal of producing 4.5 million drones per year. Russia deploys thousands of loitering munitions each month, including Iranian Shahed designs. This is saturation warfare. The logic isn't to create a weapon that can't be intercepted. It's to generate attacks dense enough to exhaust the defender, both economically and psychologically. Consider this calculation. A modern interceptor missile costs roughly $3 million. A target drone may cost $30,000. That's a 100-to-1 exchange ratio. You're spending 100 times the attacker's budget to destroy plastic and commercial electronics. It's the equivalent of burning down a forest to retrieve a single branch. China has taken this further with projects like the Zhuzhen drone carrier, which conducted its first test flight in December 2025. Carrying and launching up to 100 drones at once. In this kind of warfare, victory doesn't depend on superior technology alone. It depends on which side can endure longer in a contest of financial and industrial attrition. Chapter 3: Why lasers are strategic. So, why is Japan placing its confidence in laser technology? Japan's Acquisition Technology and Logistics Agency is operationalizing a concept known as the low-cost interceptor. In saturation warfare, lasers offer 3 critical advantages. First, reversing the economic trap. Each laser shot costs only a fraction of what a traditional interceptor requires, avoiding scenarios where millions are spent defeating cheap drones. Second, effectively unlimited firepower. Unlike missile launchers with finite magazines, a laser can keep firing as long as the warship supplies stable electrical power. No risk of magazine depletion. Third, reaction at the speed of light. Lasers minimize delay between detection and engagement, providing a decisive advantage against close-range threats with irregular flight paths. The 100-kilowatt system on JS Asuka represents a practical step toward validating fleet defense at sea. Tokyo's objective isn't to replace missiles entirely. It's to construct a layered defensive architecture. Lasers clear low-cost targets at short range, allowing expensive systems like the SM-2 and SM-6 to focus on higher-end threats. Chapter 4. Looking to the United States. To understand Japan's ambition, you need a reference point. The U.S. Navy's Helios, high-energy laser with integrated optical dazzler and surveillance. Helios isn't a tech demo. It's the first truly operational laser weapon deployed on a guided missile destroyer, installed on the USS Preble at 60 kilowatts. Japan's system is still in sea trials, but at a higher threshold, 100 kilowatts. Even so, both are early steps. The U.S. Navy is aiming for 300 kilowatt class systems in the future. The core difference between a test weapon and a combat-ready system is integration. Helios ties directly into the ship's Aegis combat system and SPI radar. A tactical action officer can select the laser as an engagement option on the console, receive targeting data, and fire with precise coordination. Helios demonstrates real value through a 3-in-1 mission set: Hard Kill. A high-energy beam can physically disable or destroy drones or fast boats within seconds. Dazzler. A non-lethal option to overwhelm or blind adversary optical sensors, like an extremely high-intensity glare weapon. Surveillance. High-resolution cameras and thermal sensors identify targets and assess damage without demanding more from the ship's primary radar. During a Pacific test, the crew aboard USS Preble demonstrated Helios against an unmanned aerial target. Once the SPY radar generated a track, Aegis established the engagement solution. Within seconds, the laser beam turned the target into a fireball in the night sky. A warship had successfully brought down an aircraft using directed energy under realistic conditions. Chapter 5. Technology and Core Challenges. The idea of continuous fire made of light sounds ideal, but physics imposes hard limits. Engineers face 3 fundamental problems: power, heat, and the atmosphere. The power efficiency barrier. To generate a 100 kilowatt laser beam, a ship must supply at least 300 kilowatts of input electrical power. On older destroyers, finding that excess power is difficult. Generators are already heavily tasked by high-demand sensors. The thermal management problem. If roughly 30% of input energy becomes laser light, the remaining 70% becomes waste heat. Without immediate cooling, components fail rapidly. In some designs, the cooling system occupies more volume than the laser mount itself. The atmosphere and maritime environment. A laser can't fire and forget like a missile. The beam must stay concentrated on a single point for a specific dwell time. But water vapor, salt spray, and turbulence distort and scatter the beam. Ship motion and sea surface reflections complicate fire control further. These constraints draw a clear line. Lasers are not yet a full replacement for missiles. They're emerging as a critical complement in managing saturation warfare. Chapter 6. The Global Directed Energy Map. Japan and the United States aren't alone in this race. United Kingdom, Dragon Fire, demonstrated the ability to hit a coin-sized target at half a nautical mile. Britain's advantage is extremely stable beam control. Israel, Iron Beam. Designed to complement Iron Dome, focusing on short-range threats like rockets, mortars, and drones at lower cost per intercept. China, Liao Yuan. 1. Reports claim it could reach 180 to 250 kilowatts, potentially above current operational systems. But figures remain unverified. Russia, Parisvet. Assessed to prioritize disruption and dazzling of reconnaissance satellite sensors rather than destroying drones. Closing. The future of fleet defense. What we're seeing isn't just equipment testing, it's a redefinition of what it means to defend a fleet. In an era where industrial capacity can produce millions of low-cost drones every year, victory no longer belongs to the side with the most firepower. It belongs to the side that can sustain financial endurance and magazine depth. Lasers change that balance. With low cost per shot and near inexhaustible magazines, they provide a path out of economic exhaustion. But physics still sets boundaries. In the near term, their role is to serve as a complementary defensive layer, integrated with networks like Aegis to maximize survivability against saturation attacks. In the conflicts ahead, controlling cost and endurance could prove as important as controlling firepower.